Hello, this is Brian Kinghorn, and I'm talking on the last of 4 videos on preparing your parameter files, and this is advanced operations in grouping. And this is the example we had in the last video. We've got 4 female groups in red and 3 male groups in blue, and one of the male groups is made up of 2 subgroups. Essentially, these 4 female groups are different farms, and the male groups 11 and 12 are probably either on the same properties or different close-by farms for bulls for natural mating, and 13 and 14 are AI stations and therefore can be mated anywhere. And as you recall, we are not permitting mating across these different states because of geography. And the reason we're pulling this all together in a single analysis is that this would be a breeding operation which is a single enterprise, and in which diversity should be managed collectively in order to help safeguard future genetic gains for this important breeding operation. And this is where we ended up in the last video with the results for the groups here. These are the female groups, the 4 different farms, and male groups are shown in this column here. And one of the 3 things I pointed out that may make you unsatisfied with this result is that, for example, Cameron from group 11 is used in 2 different farms simultaneously, and if this is a natural mating, that's not possible. And likewise for group 12 bulls, they are also used in 2 different farms simultaneously. So that is something we can fix now. If we go to our InpGroups.txt file and look down close to the bottom, we can see there's a male natural mating vector. So if I put in a 1 for group 1 and group 2 and save that, I can come back and make a run. Stop this run, and I'll come back in a moment. It's close to convergence. I'll click this update button, and here we can see that Cameron is used just in 1 group, and the group 12 bulls, these 3 are also just used in 1 group because they're natural mating sires. So that looks pretty good, but we may be a little bit unhappy with the distribution across groups. We are seeking a large number of matings in group 4 because of reproductive technologies being used there. What we can do is go to the InpGroups.txt file, and we can see that here. MateCell is quite happy that it's given us what we want, which is 20 matings in group 1, 20, 20 and 100 in group 4. But we're not happy with the distribution, so what can we do about that? What we can do is specify a target for each combination of male and female group for the number of matings that we desire. And with the artificial insemination group, it's going to be largely driving the IVF program in group 24, so we're looking for a large number of matings in that. So we need to specify that to MateCell, and we can do it with this feature here where we can set targets for group matings. These lines at the bottom of InpGroups.txt are optional. If you don't include them in the file, then that's all right. MateCell will go ahead but not exploit those features. So if we put a weighting here, and it is a weighting, so the default of 1 is what's recommended, then MateCell is going to target those numbers of matings per group combination. So I'll save that and come back to our run and create a new run, and I'll be back in a moment. And I'm going to click print matings prematurely for a reason that you'll see. So here we have our natural mating is being adhered to, and with group 13 and 14 we have mating across groups. So let's go and look at our InpGroups.txt file. And you'll see that the numbers that we are targeting, shown over here, are not being quite well achieved at this stage, because this process is operating like a soft constraint and giving rewards to solutions that fit better. And because I clicked early in the process, we didn't get very good convergence. So let's let this converge a little bit better. So that's gone for a while. You'll notice it's not getting all that close to the frontier. There's a little bit of a difference there, and that's because the frontier is built without the constraint on those numbers of matings per group combination. So let's have a look at the result there. We get something similar over here on the individual sire by group, but if we go to the file, we can see the group by group combinations, and we're getting what we want except for this last column where we're wanting 10 and 90 matings as seen over here, but we're getting 30 and 70, and that's because we're not pushing hard enough in this issue. Why are we getting 30 matings here for group 2? Well, if we go back and look at the results here, We can see these 30 matings are all coming from Wayne. He's the highest indexing animal and he's being used to the max, and so it's a question of competition between getting good index results and getting what we want in the mate allocations. There is something we can do about that. If those mate allocations are critical, we can increase the weightings, but there is actually a better way of doing this. And that's as follows. If we go to InpGroups.txt, we can actually force these results simply by typing in the word force there. In this case, the weighting is not mattering. If it's a 0 or a 1 or anything, it's ignored. What's going to happen is that the algorithm is only going to consider solutions that totally adhere to what your constraints are there. So let's try that example. So that's converged. We can now see that Wayne's only used 10 times. And I should point out that the numbers we've used in this small example are for quick illustration, and that for an example of this type we would typically be looking at many more animals involved. Let's look at the results, and we can see we get perfect adherence to what we asked for. And just to remind you, that is because we used the word force and it forced these results. Now there's an important way that MateCell is operating here. I'll talk about this a little bit more at the end of this video, but basically MateCell is only allowing legal results to get through to evaluation. You roll the dice and MateCell looks at the numbers and generates from those a legal solution. Whereas what we did before when we used no forcing was to let everything go through and then penalize the solutions that didn't adhere to what we wanted. This fixing strategy, as we call it, is much more efficient and much faster. And the reason for doing this is to give dramatically increased speed for large and complex grouping problems. And this has made quite a big effect for this recently introduced feature. Okay, for this last feature, I've chosen to make a run at 45 degrees because it illustrates it better for this small data set where we've got rather small numbers. When we make this run, let's have a look at groups 13 and 14, the AI sires. So we're going to be sending semen into 4 different groups, and it is practically inconvenient for the operation to send a single dose of semen, or what is required to make a single insemination, to these different farms. So these ones here are practically not so useful. A 0 is okay because there's no postage involved. So what can we do about that? We have this feature, filter and waiting for male min use per group. So that means that if a male is going to be used in a group, we want to use it a certain number of times. That's not the same as the normal min use, which you see up here, which is the number of uses for a male across all groups. This is the amount of use of a male in a single group. So we have targets set for that, and the min use per group for the last male group is 5 for each female group, and we can put any numbers in the boxes there. I've just chosen to keep them all at 5. And if you read the manual, there's a filter, which is a fixing type of approach as described earlier for forcing group matings, but there is also a weighting, which you'll see later in the video. That can be quite useful too. So let's save that and make the run. So here we have a set of results, and we're looking at groups 13 and 14, so it's these last 4 lines. And you can see that if a male is used anywhere in any group, it's used at least 5 times, and the rest are zeros. So this is purely for practical operations that you can set these minimum constraints, and I'll move on to show you a more realistic example of that. So here is that more realistic example. And for this run, I set the filter and weighting to 0, so we're not using this feature in this base run. And for this set of data, I'd like to thank James Taylor from Sheep Genetics, which is the group that's responsible for driving genetic progress in wool and meat sheep in Australia, and Meat Elite Australia, a very progressive group of sheep breeders. And in this case, we have 13 different flocks, and we have a number of individual males. And what we're looking at is artificial insemination for the target number of matings in each of these flocks. Now you'll see there are many cases where a ram is only used once in a flock, and that's not desirable. Of course, technically the result that we see here will be compromised to some extent by moving away from just having a single or a small number of matings per flock, as we're just about to do. So what happens when we change this filter and weighting here? Here in the next slide, I've done that. The filter is set as a switch to 1 and the weighting is set at 1, and these are the recommended starting positions for this. And you'll see in the result that each RAM is used at least 5 times, or 0 of course, in each flock, and that's what was desired. And if we look here, if I roll back to the previous slide and then back to this slide, you'll see there's a small compromise in the technical outcome as a function of getting this practical result. Let's go a bit further, and if we look up here, we'll see that if I go to targeting a male min use per group of 10, and I'll just switch on the filter at this stage, leaving the weighting at 0. And here you can see that it's generally a good result. In most cases, the males are being used at least 10 times, but there are cases of 7s and 9s and 5s. And that's a reflection that the filter is not completely foolproof and does not guarantee the result that you want in each occasion. And that's why we've added a weighting as well to help fine tune that. So let's go and look at the results where we apply a weighting as well with the default value. And now we can see that we get perfect adherence to our desire of at least 10 uses per flock or 0. Just like min use per animal, except this is min use per female group. Now, if we look at the result here, we can see if I roll back, you get less compromise, and there is the uncompromised result with no constraints at all. Another way of doing this is to go forward to where we were and go and do the same run. If you look at the front here, it's the same, but if I import the solution from the technically unconstrained run, that's how much compromise we're making. And so to achieve the result we had in the previous slide, I'll just go back to look at it. This result here with the pattern of mating, which is a deviation from no constraint over here, as shown on the screen when you import a solution. There's the compromise in index and, in some extent, diversity that we get. So there's a choice to be made as to what level of constraint you want to apply in terms of the compromise you make technically in other components. So I'll finish with a description of the methods involved here, only briefly. This is a graph of a mate selection analysis, progressing with evolution of those number of generations on the x-axis, and the y-axis shows the fitness, how good the solution is according to an objective function. And there are two basic methods here. The fixed one is the line at the top, and the penalizing method. There are 4 different examples down here. So the penalizing one, you can conceive of it this way. The raw material that is evolved, the raw numbers, you can think of as a roll of many dice, and you see these numbers and you convert them into a mate selection solution, which is actual matings between individuals. You look at that solution and see how many matings there are that are breaking the constraint for grouping. So how many matings involving groups that are not allowed to mate with each other, and then penalize according to that. And the penalty weight, I've got different ones here. We take the weakest penalty weight, that's this blue line, and there are gaps in the line wherever the solutions are breaking the constraints, and the line is solid wherever the constraint's being met. This best strategy here with a weighting of 0.01 is this one here, which is actually what we used in the old TGRM. And it looks as though it's coming to some kind of a convergence, but it's not at all. This other strategy, the fixed strategy, which we originally used in MateCell, is doing much better. Most of the evolutionary pressure here is being used to maintain legality for the different constraints. And we thought we were doing quite well until using it in a more complete scenario in pigs and discovering that the results were not sensible in some respects, and that was because we weren't getting convergence. So we had to move towards a new approach. And that approach is described in the paper at the bottom of the screen. And you can think of the raw solution being a roll of many dice. In this case, when you look at the numbers, they're put through a filtering system which ensures that the result at the other end is legal with respect to the constraints on grouping. And that's what we originally used in MateCell. We've moved beyond what's in that paper now and built in better speed and robustness by keeping to the same philosophy but changing that algorithm quite substantially in parts. And so you can see the dramatic improvement in performance. So to get to this level of fitness as we used to, that now takes about 1,000th of the number of generations. And that means that we can concentrate on evolving what really matters and not evolving legality. And that is fully true for the core algorithm for grouping, which comes as far as the group mating permissions. You'll see that further down with the forcing of targets, that is also a fully fixed strategy. so that there is no need to maintain legality through penalisation in that one. But if we don't use the forced option, that is purely using penalisation, and that's why it can be very slow for bigger and more complex jobs. And so the forcing strategy has made a dramatic improvement for some operations. And the last feature that we just looked at, the group min use feature, is a hybrid approach. And so if you manage to get away with the filter working for you, that operates very quickly. If you have to resort to using the weighting as well, that can slow down operations a fair bit. There are other components in MateCell that we use a penalising strategy for, and we aim to move those onto a fixed strategy to get greater speed. A key example of that is the threshold on inbreeding levels, and that has caused slow convergence in a number of cases, and there are plenty of warnings in the manual about it. But we will be aiming to make that at least a hybrid, if not a fully fixed approach, so that we maintain higher speed and robustness for use of that. So that's the end of this video. Thank you for listening.